welcome everybody to Physical Science today. This is a copy of a student's graph of what we did yesterday. Now this graph came from data that was given to us on a piece of paper and said, here, graph this data because this is what happened in an experiment. And so then what we decided to do is at least see part of this in our lab yesterday. So the part that you guys saw yesterday would have been about this part, right? Is that about what you, now look at your data and see, is this kind of what you're seeing in your data? Yeah. Okay, and most importantly, I want you to see this flattening out here. Okay, so this is flattening out at 100 degrees Celsius. Yours now is different. Tell me what some of the flattening out pieces, or what temperature flattened out for you. Okay, so it sounds like everyone got a little bit above 100. And if you think of what we did yesterday, we had our beaker. We had our beaker, and then we had our thermometer sticking in the water, okay? And down here then is, what was happening to the thermometer right down here? It's temping the water, but it's also touching the glass too, right? Yeah. Now, I guess I'm not exactly sure if that's why it was hotter or anything, because you'd have to do some studies to see the effects of that. But I could think in my head that, hey, that might be a reason why it was temping higher than 100 degrees Celsius. Or it could have been just that the thermometers weren't really very accurate. Because I do know that in Bismarck, the temperature of boiling water is not 100, but instead, what is it going to be? Do you think more or less? Now,
98.
Okay, that's right. How do you guys all know that? Oh, I did? Oh, okay. Well, in earth science too, okay, what keeps the gas dissolved in the water? And so I'm talking gas, nitrogen mostly, oxygen, and then H2O gas too. What keeps it dissolved in is a pressure that's pushing down. What pressure is pushing on that liquid? There's a force of gravity that causes this pressure to happen. Without gravity, we wouldn't have this.
Buoyant force.
What's flying around up here all over the place?
Nitrogen.
Mostly nitrogen, very good. And that nitrogen is moving really, really fast, and nitrogen particles are hitting at all different spots along the surface of the liquid. Do you agree with that?
Yes.
And you add up all those tiny little forces, and you get a big force. And if you turn this beaker on its head, you'll see up here there's an area, right? So that's the top of the beaker. There's an area of water that's getting hit on by all the nitrogen pieces. So that's a force per area. What is that called? Pressure. Force per area. So when we talk about air pressure, it's because of all the little pieces that are actually bombarding us, or in this case, they're bombarding the liquid. So when something boils, what happens is the little water particles in here jiggle around fast enough, and they push outwards, and once they hit a fast enough force per area of this bubble inside that is equal to the force per area on top of the liquid, that's when it turns into vapor, and that's when something boils. Now, why would it boil less than 100 degrees up here in North Dakota or in Bismarck? Because the pressure, yeah. So like, if this is our, kind of the top of our atmosphere, which is very, very high, maybe the clouds are way down here, and then maybe the Earth is like right there, and that's the top of the atmosphere. You have a whole entire column of particles that increase in density as you go down. I can't do that many particles, but it gets much more dense as you go down, because there's these other particles sitting on it, right? So down here now, we finally have our beaker that gets pushed on. That's a big, huge beaker. What if we go up? Like Bismarck is like 1,650 feet above sea level, or 1,750, depending on where you're at. It's around 1,700 feet above sea level. Well, that means that this column here that extends down to sea level, that gives us 1 atmosphere of pressure, that means you're missing this much of that column, and so then you're missing that much of the particles that are on top of the liquid. Well, if there's not as many particles up here, you know, our beaker up here, which of course this is a huge beaker, if there's not as many particles hitting the liquid, there's less force, and then there's less pressure, which means in order for there to be a boiling, you don't have to match the same amount of pressure. And if you don't have to match the same amount of pressure, you don't match the same amount of force, and you don't match the same amount of velocity of particles, which ends up becoming temperature. So if you go up here to Denver,
Colorado.
that's a Mile High, right? Mile High Stadium. It boils at much less than it does here, too. I don't know what it is, like 90 maybe or something like that. And then if you keep going to, you know, Aspen, I don't know how high Aspen is, but the mountains get pretty tall there. Right outside of Denver, they get up to, I don't know, over 10,000 feet pretty quickly. Well, how do you boil stuff up here? Well, with much less heat. Like maybe it's only 78 degrees Celsius, or I'm not sure what it is. But you know what happens? Then the water doesn't get as hot. You don't cook the food as fast. So what do people use up here usually, or a lot? These little things called pressure cookers. Have you ever seen them?
Yeah.
And if your mom or dad can things, you put the stuff inside the pressure cooker and you seal it up. And then what happens is it keeps the gas inside here, and so then the gas becomes added to the atmospheric pressure inside the container. And then the boiling, you can raise it up to higher than what it would be because of atmospheric pressure. Okay. So back to what's happening here. So let's look at the first part of this graph here. This is down at -2. Well, okay, so the reason why we didn't do this in the lab is because it's really hard to do this in our kind of lab. Because you'd have to have a thermometer that could temp in the ice. So whoever, what? Well, yeah, I'm not sure. I've never done it myself. I've never done it even in college, or I've never done it before. Not sure how that would work. It would have to freeze in though at some point, right? Well, what happens right here then? This is really the interesting piece is right here. Because we see that that's the change from the frozen. Maybe I should change colors here. I'll say blue is the coldest, right? And then right here, what's actually happening along this line? Did anybody know? What? At that part, it's melting. So what happens is I get these water molecules, okay? So that's what they look like, okay? And then I got another one sitting over here because the hydrogens are partially attached to the oxygen of the other molecule. And, of course, I can never do this perfectly. But this would be an ice particle. And it would be in a regular crystalline pattern, which I didn't do a very good rendition of a regular crystalline pattern. You know, the solid, it should be everything spread out evenly. Now these particles here are wiggling and jiggling around, but they're staying in the same spot. Because that movement always happens unless you hit absolute zero, we think. That's what our theory is. We've never gotten there. But these are wiggling and jiggling. And so there's an attraction from the hydrogen to the oxygen of the next molecule. And that's what kind of like locks it into place. And if they don't wiggle too much, then they remain in a set position, but they wiggle and jiggle. But there's energy associated with it. So it takes energy right here to like bond this stuff together. So there's energy that's wrapped up in the bonding of the crystalline structure. Now bonding isn't like the atomic bonding, but it's a crystalline bond. And what happens here then is, because really what am I doing? At this point here, am I adding or subtracting heat? I'm adding heat there, right? What am I doing right here, this part? Am I adding or subtracting heat? Okay, so now we have to distinguish between temperature and heat a little bit more. In this part right here, these bonds of these hydrogens and oxygens, they're like solidified together. If something is glued or stuck together, do you have to take energy to take it apart? Yeah. So I am also adding heat here too, but instead of the heat increasing the temperature, which is the average movement of these particles, the average kinetic energy, what that heat does is it breaks this bond. So it's like kind of if you have Velcro and you have to rip something apart, you use energy to do that. That's what's happening right here, is the heat energy is used to take these big pieces away from each other. So that's why we don't see an increase in the temperature at this part, because the energy is used to take this crystalline structure down. Okay? So, at this point here, then, this is called, at this point, we call that the latent heat of fusion. So you got to know that for later. The latent heat of fusion. Now you think, well, that doesn't make sense because it's going the opposite way. But why should it be called the latent heat of fission, maybe, or unfusion? But why might this area be called fusion, would you think? Well, if I'm going up the graph this way, if I'm going up the graph this way, then what happens at this point? You need to know what that point is called if I'm going up the graph. What happens to the ice? Melting point, okay? So that right there is the melting point, okay? Well, what if I'm going down the graph? What happens there? That would be the freezing point, right? So that's where this whole latent heat of fusion, or sometimes they just call it heat of fusion, I guess. They call it latent because it seems like the temperature is not increasing with the heat increase. That's why they call it fusion, because if you go down, it's fusing these particles together, but it just so happens that the melting point and the freezing point is the same point. You guys understand that? You have to know that for the test and all the stuff for the test. So it's labeled fusion, but it's for both melting and freezing. Okay, so let's keep looking here. I'm going to move some of these pieces away so you can see, pay attention to other things. Okay, so right here, then we've got this whole phase. So right down here we had solid here, right? And then here we have part solid and part what? Liquid. Okay. And then, but this whole piece here though is all liquid, right? So what is happening on the way up? Am I adding or subtracting heat at this point? So heat here is going in on the way up. If I was going down, then heat would be going out. Okay, so that's some physics stuff that you'll pay attention to second semester. Okay, and then finally, we get to the hottest part right here. So what's happening at this piece? It's vaporizing. Okay, so the big question is, why did that never get any hotter than 105 degrees or whatever you measured? Why did it not?
Because before it could get hotter, it would already be a gas and already would have left.
That's exactly right. So you have your thermometer in the liquid, right? The hottest that this liquid can get is called bits, and you need to know this. This is called the, this flat area. What's it called when we go from a liquid to a gas? You remember that name? It's called vaporization. Vaporization. This point here, what do you think it would be called? Judging by what we call this down here, what do you think this this area would be called? What's happening there?
Vapor.
The heat of vaporization. So this was the heat of fusion happening here, and then this is the heat of vaporization. So all the heat that's added at this point then is going into canceling out the attractive forces in the liquid water. Okay, yeah, so when this gets to be, if this piece of water gets to be 100 degrees or 105 for you, well then it leaves as gas. And so that's why it's actually everything that's in here is going to be at least 100 degrees Celsius or less. Otherwise it would be gas and it would escape. Okay, so that's exactly why we can only tempt that. Okay, but we have this to show that this data was good from our lab. So the things that we have to know about this. Melting point and freezing point are the same. Okay. Vaporization point and condensation point. Okay, that's another word you need to know. Condensation point would be the same. Okay. It's just if you're adding heat or subtracting heat. Do you guys have any questions about this? Okay, well, that should help you with your assignment for today.